The physical world produces a constant, chaotic storm of electromagnetic noise. When a sensor or antenna captures a signal, it doesn't receive a clean, singular wave. It picks up a messy, overlapping composite of countless different frequencies vibrating all at once. To make sense of that chaos, we use filters. By deliberately manipulating the physical impedance within a circuit, an engineer can extract specific, desirable frequencies while systematically destroying the irrelevant noise around them. This schematic visualizes 4 primary filter archetypes. On the left, an original, complex wave breaks down into individual frequency components. Following the paths to the right, each frequency routes through a specific geometry: low pass, high pass, band pass, or notch, isolating the exact wave it's designed to catch. Whether we need to extract clear audio data or stabilize a direct current power supply, engineers have to architect these circuits to act as precise frequency gatekeepers. In theoretical math, a filter acts like a brick wall. A signal hits a predefined threshold, and the filter drops it to 0 instantly in a perfect vertical line. Look at this low-pass response graph. Physical components can't switch off instantly, creating a smooth curve. This divides the circuit into 2 zones: the allowed pass band and the rejected stop band. High pass, band pass, and notch filters all share this physical limitation. Because we can't build a perfect brick wall, the primary objective of active filter design is to force that practical physical curve to drop as steeply and mathematically close to a straight line as possible. To measure how steep that drop is, we track the circuit's performance by plotting its voltage gain against a logarithmic frequency scale. This chart maps a first-order low-pass response. On the x-axis, FH establishes the cutoff boundary. On the y-axis, gain drops by 3 decibels to 70.7% of maximum voltage. At this -3 dB point, total signal power is precisely halved. The location of that boundary isn't arbitrary. It is established entirely by the physical properties of the passive components in the circuit, specifically the values of the resistor and the capacitor. Cutoff frequency equals 1 divided by 2 pi RC. If an engineer wants to move the boundary, they simply swap out the physical resistor or capacitor to shift the math. That -3 dB inflection point is the exact moment the physical hardware stops transmitting information and starts destroying it. Relying solely on passive resistors and capacitors introduces a structural flaw. Passive networks strictly attenuate. Even the frequencies you deliberately want to keep inside the passband will lose signal strength just by traveling through the circuit. There is also a secondary problem. If you connect a purely passive filter to another circuit downstream, the combined external impedance changes the math. You accidentally alter your carefully tuned cutoff frequency just by plugging it in. To fix the voltage loss and the impedance shift, we combine the passive RC network with an operational amplifier, transforming it into an active filter. The op-amp does 2 things. First, it provides passband gain, physically amplifying the signal back up to full strength. Second, its inherently high input impedance acts as a buffer, completely isolating the sensitive RC tuning network from any downstream load. When paired with a specific tuning configuration known as a Butterworth characteristic, the op-amp ensures the amplified passband stays perfectly flat, eliminating voltage ripples that could corrupt the data. By introducing that single active component, a leaky, fragile passive attenuator becomes an isolated, mathematically precise signal processor. Even with an op-amp, a standard first-order filter has a problem. Its transition band still decays relatively slowly into the stop band, letting adjacent noise bleed through. If we check the curve again, a first-order circuit reduces gain by exactly 20 decibels for every decade, or 10-fold increase of frequency past the cutoff point. To sharpen that cut and reject the noise faster, engineers increase the filter's order. This means physically adding more sequential RC networks into the input path. Upgrading the circuit to a second-order filter exactly doubles the steepness of the stop band rejection. On this second-order response graph, the result is clear. The transition line plunges twice as fast, killing the signal at a rate of 40 decibels per decade. Filter order gives the engineer a mechanical lever. Stack more components, compress the transition band, and aggressively block any noise sitting near your target frequency. We are not restricted to just cutting off high frequencies. By taking the foundation of a low-pass circuit and physically swapping the positions of the resistor and the capacitor, we completely invert the circuit's behavior. This active high-pass schematic puts capacitors in series with the input and resistors to ground, blocking low frequencies. With 2 capacitors and 2 resistors, it's a second-order filter, feeding directly into an op-amp for active amplification and isolation. Once you have individual high-pass and low-pass blocks, you can wire the output of one directly into the input of the other. In engineering, this is called cascading. If you cascade a high-pass filter into a low-pass filter and make sure the low-pass cutoff is set at a higher frequency than the high-pass cutoff, you create a bandpass filter. You don't need entirely new physics for different tasks. Complex filter topologies are simply modular, cascaded combinations of those foundational RC and op-amp building blocks. Filter design rests on 3 architectural pillars. Passive components dictate the exact frequency boundaries, active op-amps maintain the signal strength, and the filter order dictates the precision of the cut. When we plot a cascaded circuit, we can watch those pillars go to work. The high-pass and low-pass curves slide together. Where they intersect, they carve out an asymmetrical, strictly defined bandwidth in the center of the spectrum. This exact math is how audio equipment separates low rumbles into a subwoofer and high notes into a tweeter. It's exactly how digital converters filter out high-frequency noise to prevent aliasing errors in software. Whether tuning a radio receiver to a single station or scrubbing ripples out of a DC power supply, the operation relies on deliberate, mathematically precise attenuation. Circuit design is simply the physical manifestation of mathematical limits. By manipulating those limits, engineers sculpt the exact frequency profiles required to isolate usable data from the chaos of the physical world.